Hello and welcome back to our continuation of statistics and probability. In this video lesson, we will address the normal curve and use the normal curve to approximate probabilities of things happening. Let's get started. Before we do anything, let's address the definition of the normal curve. The normal curve is a specific type of data distribution. Shown here, you see three different data distributions. The normal curve is the one in the middle. It is also known as the bell-shaped curve because it is in the shape of a bell. The distribution on the left is a negatively skewed distribution, or a distribution that is skewed to the left. On the right side, you see a distribution that is skewed as well, and it is skewed to the right. It is possible that a data distribution follows one of these three distributions shown here, but it's also possible that they do not follow any specific distribution at all. So when we look at a distribution, we first need to decide whether it is a normal distribution or not. In fact, many things in the real world follow a normal distribution. Let's take a look at an example or two. Some real-world examples include the heights of males, test scores on maybe the ACT or the SAT, blood pressure for adults, or even calorie intake. Let's take a look at what this looks like on the normal curve. For our example, we're going to take a look at test scores and how they can follow a normal curve. I'm just going to make up some numbers. Let's say that we gave a test to 100 students and the average test score was an 80%. Since they follow a normal distribution, we know that the average score is going to fall right in the middle of all of the test scores. So that would be our 80%. This average is an average for a population, or all of the people that took the test. We call that mu. So our mu, which is the symbol for average of a population, is 80. Now, something else we want to talk about with our distribution is standard deviation. The standard deviation is a measure of how spread out the data is. The larger the standard deviation, the more spread out our data is, and the smaller the standard deviation, the more compressed the data is. For this example of test scores with a mu of 80, or an average test score of 80, let's just say that we have a standard deviation which is sigma, and this is the symbol, of 5 points. Now we know, since our data is distributed normally and our average is 80, we have 50% of test scores falling below 80%, and the other 50% of test scores falling above 80%. It's normally distributed, or symmetric, so we have the same weight on each side. What the standard deviation tells us is that for each standard deviation, we have another proportion of the population. Let's make it a little more clear. So I'm going to count up to 3 standard deviations away from our mean. So increasing by our standard deviation, we would go from 80 to 85 to 90 and 95. Continuing on the left, we have 75, 70, and 65. Now that we have the standard deviation and the mean on our normal curve, this leads us to the empirical rule. The empirical rule is the 68, 95, 99.7 rule. What this rule states is that 68% of the distribution is within 1 standard deviation from the mean, 95% of the data is in between 2 standard deviations from the mean, and 99.7, or almost all of the data, is in between 3 standard deviations of the mean. Let's take a look at what this looks like on our normal curve. With mu being the center of our distribution, or the average, we know that 1 standard deviation to the left and 1 standard deviation to the right of that average, 68% of the population live. Between 2 standard deviations from the mean, 2 to the left and 2 to the right, 95% of the population live. And finally, 99.7% of the population are in between 3 standard deviations to the left and 3 standard deviations to the right of the mean. Let's take a look at what this means in context of our test scores example. Using the empirical rule for our test scores example, we see that 68% of the population who took the test scored in between 75 and 85%. Similarly, 95% of people taking the test scored between 70 and 90%, and 99.7, or almost everyone, scored between 65 and 95% on the test. Since we know 68% are in between 75 and 85, and we also know that this distribution is symmetric, or a normal distribution, we can say that half of our 68 are to the left, or in between 75 and 80, so 34% scored between 75 and 80, and the other half of the 68 is in between 80 and 85. So 34% of the population scored between 80 and 85%. Similarly, we can break up the 95 and the 99.7. Breaking up the 95%, we have 47.5 to the left and 47.5% to the right. And finally, the 99.7, we see that 49.85% scored below 80 and 49.85% scored above 80. Let's look at an example. Our example reads, suppose that the heights of students in an online math class are normally distributed with a mean of 60 inches and a standard deviation of 2 inches. Whenever we hear normally distributed, we want to sketch a normal curve and place the mean and standard deviations on our picture. I have sketched the normal curve and placed the mean, 60, and the standard deviations, 3 to the right and 3 to the left of our mean on our normal curve. Now let's take a look at each question. The first one says, what percent of students are between 56 inches and 64 inches tall? 56 inches is this measurement here, which is 2 standard deviations to the left of the mean, and 64 inches is 2 standard deviations to the right of the mean. With our empirical rule, we know that 2 standard deviations to the left and to the right, we know that 95% of the population are in between those two numbers. So we know that 95% of students that are taking the online math class are between 56 and 64 inches tall. The second question is, what percent of students are taller than 60 inches? 60 inches is our mean in this problem, so we know that half of the population are taller than 60 inches, so our answer would be 50% of the online students. The final question addresses the percent of students that are shorter than 58%. So we're actually looking for the percent of students that fall in this shaded portion here. We know that between 58 and 62 inches, 68% of the population lie. That means that on the outside, meaning this shaded portion here and this shaded portion here, we have the remaining percent of the population. So taking the total population, 100%, and subtracting this 68, we know that on the outside of 68% lie 32% of the population. Half of that 32 must be here, and the other half of that 32 must be here. Therefore, we know that 16% lie on this side or in the shaded area. More specifically, we can say that 16% of the students taking the online math class are shorter than 58 inches tall. What about the percent of students that are taller than 61 inches? We try to use the empirical rule, but 61 falls in between 1 standard deviation from the mean. So the empirical rule doesn't really work in this case. It makes me very sad. What we need to do is come up with a standardization for our heights along this axis here on our normal curve. In order to do that, we will use our formula for a z-score, where z is equal to x minus mu divided by sigma, where x is the observed height, in this case 61 inches, minus the average height, which would be 60, and then divide that by the standard deviation, in this case is 2. Our z-score for this example would be 1/2 or 0.5, which means that our height of 61 inches falls a half of a standard deviation above the mean. Now we'll use technology in this case to find the percent that fall above 61 inches. To have the calculator give us our answer, we will hit second variables, which takes us to distributions, and arrow down to normal CDF, or normal cumulative density function. And the order for our notation here, we'll just go ahead and type in -4. This is the lower bound for standard deviation, and our upper bound for the standard deviation is 1/2. That is our z-score where we want it to stop. So I'll enter the 0.5, and then I'll hit enter. The number that we have is from the left side up to our z-score. And the calculator gave us the number that was 0.6914. This number represents the sum from the left all the way up to our z-score of 0.5, or the 61 inches. We know that the 0.6914 is 69.14%. Our question is how many are taller than 61 inches? So what we're looking for is this yellow shaded area. We know the total has to be 1. So if I go ahead and take 1 minus our answer, we will have our yellow shaded area, which is 0.3085, or approximately 30.8%. So we can say that 30.8% of students in the online math class were taller than 61 inches.